This lecture is about green, sustainable, energy efficient, cost effective refrigerated storage facilities. So, what do we have here? We'll talk about refrigerated warehouses and how they fit into the farmer to the consumer chain or pathway, cold chain. There are other things that are in that cold chain, the cooling facility itself, as well as any trucking, shipping, or other transportation system. Most refrigerated warehouses operate in the range of about -10 to +40 degrees Fahrenheit. There are exceptions to that, but that's a general range. Electrical energy is used to operate the refrigeration equipment in the vast majority of cases. There are refrigerators that can run on propane or other fuels as well. Oops. So it's important to look at refrigeration because, as we already know, refrigeration is very energy intensive. And if we look at global energy consumption, refrigeration and transportation are right at the top of the list. In 2018, the USDA estimates US refrigerated storage capacity at 3.6 billion cubic feet. That is a lot of storage, increasing at about 1% per year. The Department of Energy estimates energy consumption to be about 20 billion kilowatts per year. So when we're talking about just electrical consumption, refrigeration, cold chain management is right near, if not the top electrical consumer. And don't worry about memorizing these charts, but certainly if we're looking at the electricity consumption in the United States, you can see here neck and neck refrigeration with computers. And I'm not sure if these have changed in the last 3-4 years at all, but they're pretty much neck and neck for the top. And then other things like ventilation, lighting, etc. If we look at manufacturing, machinery is huge. Processes and boiler heating, lighting, etc. But you can see that the refrigeration segment is certainly a significant chunk within the manufacturing electricity consumption as well. But if we're talking about manufacturing, the majority of manufacturing is not a refrigeration intensive operation. So here, if we're looking at the entire US, you can see refrigeration is very high. In manufacturing, it's not as high because you're only really needing refrigeration for specialized processes or food. And so in the ag sector, if we just looked at agricultural and food-based manufacturing, this would be a much bigger percentage of the pie. Residential sector, space cooling, one of the highest ones, and no surprise, lighting is up there as well. Refrigerators and freezers. So if you put these two together, space cooling, air conditioning, and refrigerators and freezers together, they're a massive chunk. About 25%, about a quarter of all consumer electricity usage in the United States is related to cooling, either AC or refrigerators and freezers. So this particular project goal increased energy conservation and environmental stewardship in refrigerated warehouse industry. Development of a comprehensive best practices green guide for engineers, contractors, facility owners, and operators, plus an outreach program to spread the word about this, education, and information. What is a green, sustainable, energy efficient refrigerated storage facility? That's a facility that maintains a safe and appropriate environment for the storage of perishable food items, limits its impact on the Earth's natural resources, including both energy and water, employ elegant, simple, passive design and engineering solutions. And this is really important. You can always throw electricity and engineering at a problem, and you're using electricity and water to solve the problem. But they're passive ways by using the environment, the design of the building, the orientation to the sun, the way the building is built into the terrain, the type of materials that are used, the color that it's painted on the outside. I remember way back in the 80s, there were some refrigerated truck lines that were black trailers. That was their trademark and logo. They were black trailers with this really cool macho design on the outside. And it certainly was a lunkhead, macho, brainless decision, because what are you doing when you have a black trailer? You're absorbing energy and you're having to spend more diesel fuel to run the compressor, to run the refrigerated unit on that trailer. And you might not even be able to keep up with it if you're running a black trailer carrying food across the desert in the Southwest, any of the deserts in the Southwest or Nevada. It gets hot. So this same principle applies to buildings. If you're trying to keep something cool, paint it white. I just saw a science report on the whitest white ever made in paint. And it's believed it could save a tremendous amount in air conditioning and cooling costs or refrigeration if you're painting a warehouse. So just by the color of the roof, the color of the walls can have a huge impact. And that's what we mean by passive design and engineering solutions. You avoid any kinds of gaps in the insulation and on and on and on. Annual refrigeration loads are reduced to a minimum. So in these facilities that are following these guidelines, refrigeration equipment will operate at high energy efficiency. They are designed and constructed to be robust, strong, and reliable. They are maintainable with minimal effort, so they're practical and efficient to operate. Environmentally friendly refrigerants that minimize ozone depletion potential, global warming potential, and annual energy consumption. And we talked about that a little bit previously, but it's important to think about these things. The refrigerants that we've used in the past have had some serious problems. Some are not the best choice because they're not as energy efficient. Some have environmental problems like interacting with the ozone and depleting the ozone layer, which protects us from the sun's radiation. You know, if we're just exposed without the ozone layer to the sun's rays, and you were out there just on a normal day playing beach volleyball or something, the radiation would kill you. The only reason we can survive the direct rays from the sun, even at this distance, 8 minutes at the speed of light, it's still enough to kill you without the atmosphere, especially that ozone layer. Now, at lower levels, ozone is a pollutant, O3, or three oxygen atoms joined together into a single molecule, O3. That is what ozone is. And it's created during the burning of fossil fuels inside of combustion engines. It's generated with electric motors, and it's highly reactive. And so it's a good disinfectant. We use ozone to clean lettuce and other things going through flume water. We'll bubble ozone in the flume water, and that will kill bacteria and mold spores in the water on the surfaces of the material being cleaned. It's a pollutant if it's in our atmosphere. We're breathing it in. It's not good for our lungs to be breathing it in on a regular basis in large concentrations. It presents problems with visibility. It gives kind of an amber brownish tint to the air in larger concentrations, along with other potential problems. So we're trying to maintain the ozone layer at the outer edges of the atmosphere where it belongs, where we want it, without creating it down here at the Earth's surface where we're breathing that. So we want a refrigerant that's not going to rise up in the atmosphere and cause a reduction. The ozone molecules react with it, and you no longer have ozone to protect us. And if we go back to a lot of the refrigerants that we used throughout the 50s, 60s, 70s, they were very harsh on the ozone layer. There were also things that, when I was growing up, underarm deodorant was in an aerosol can. You push the button and it sprays out, and you give yourself a little spray under the arms. Well, the propellants used were also refrigerants, just like that demo in class with compressed air. You can have something in the can as a propellant to push the product out. In this case, it was a liquid antiperspirant deodorant product back in the day. And they banned all of those propellants that were in spray paint cans and all kinds of things. And a lot of products just stopped using propellants altogether. Other products that needed a propellant, like spray paint cans, had to come up with new environmentally friendly propellants. And propellants and refrigerants need different properties, but often they're similar types of chemicals that are used. So anyway, environmentally friendly. Don't worry about a typical facility layout. And here's some pictures of typical facilities. You can see, light colored. Could they be lighter colored still? Would that make it more efficient? If so, how much more efficient? So you're looking at sustainable structure design. So it's not just about the refrigeration. When you're looking at a green guide, you're looking at everything. What are the materials that you're using to build the walls? What kind of insulation are you using? How did you pour the floor? Everything is looked at in terms of sustainability. The refrigeration system is the focus of this presentation, but it's not the only thing. Everything in the structure should be looked at. Natural and environmentally safe refrigerants, load calculations. In other words, how much heat is going to be going into the facility that needs to be taken out with the refrigeration or heat pump unit. And that's not only a combination, or that is a combination of not only the product you're trying to cool, but the environment in which you're trying to cool it. If I have a refrigeration unit that is located in, Denver, Colorado in November, It's not that hard to keep things cold. It's probably pretty cold outside, but if I'm in Yuma, Arizona in July, August, it's a whole different load. And that depends on how much insulation, how much are you isolated based on the paint color, the materials and insulation, the fact that doors open and close, you've got to get things in, you got to get things out. So how bad of a problem, how much additional load you have in Yuma depends on a lot of factors. And then energy use and facility management. You've got to manage things efficiently. And that includes things like how do you run your operations so you don't have doors open all day on your refrigeration unit, making it extremely inefficient. Maybe you have double door systems and other things like that. Now, I would ask you to hit pause right now and read through this. I don't want to waste the time on this lecture going through one by one, but it's looking at everything to minimize heat from the outside getting in, cold on the inside getting out, and proper efficient layout and operations. And you also have to think about staging. You don't want to mix things together in a way where you've got your receiving area right next to your coldest required area in the facility. You want to lay things out where things are next to each other that are going to have a minimum impact on moving materials or the different heat zones in your facility if you do have multiple heat zones. Building orientation and microclimate, you definitely want to think about that. I've already talked about it. You want it to be aesthetically pleasing. You want the building to look nice, but you also want to think about, where am I? I'm designing not only a building for a particular city, but am I at the foot of a mountain? Am I up on a bluff or knoll? Am I down in a valley? What terrain is surrounding me? What's the layout? What's the orientation to the sun? I want it to look nice, but I also want to take advantage of and engineer and plan based on exactly where I'm building. Orienting refrigerated dock so it doesn't face into the prevailing wind. So you don't have the wind blowing. So when you open the dock or you've got seals with the trucks coming up to the dock, those seals aren't under a lot of pressure with wind blowing right into it, creating leaks. So again, orientation to the direction of wind, really important. Infiltration areas. So you look at how the building is designed. You've got not only temperature, but you've got moisture issues. So how do you design doors, windows, seams, seams between walls or walls and ceiling? How do you design that so that you have minimal infiltration? So effects of infiltration, you can see steam on the left. You can see, I believe this is actually ice buildup coming through this doorway here. It's a really hard picture to see on my screen, but from previously seeing it on a better display, I believe this was ice buildup, where the moisture comes in, it hits the cold surfaces in that freezer storage, and boom, you got ice. Doors are linked directly to productivity and operational costs. About 50% of the total refrigeration load, the amount of refrigeration you need in a facility, is based on infiltration, not cooling your product and keeping it cool. It's about infiltration due to moving through open doors and through cracks and seams and leaks. So how do you do this? You minimize the opening and closing of doors. You maximize speed of opening and closing the doors. You minimize the size of doors so it's only as big as it has to be. And you can have doors that open to different sizes. So the door opens and closes to a smaller size when that's all you need, but it has the ability to open and close to a larger size when necessary. You don't always open it all the way if you don't need that. Seals and vents and other things that can really help reduce infiltration problems. Let's take a brief break.